Our fourth and final video on pulleys is pulleys over an apex. You may not know what an apex is. You will in a few seconds. That's what I mean by pulleys over an apex. Okay, so there's a lot involved here. The questions don't come up very often, but I'm covering it just in case they do. The last thing you want is to be sitting in a public examination and seeing a question of this type for the first time. So there's the weight of A, there's the tension, the normal contact force, and find the weight components, sine down the incline, cos into the plane, and then we can remove the weight of A. Now, parallel to the plane means we can ignore the forces perpendicular to the plane. So we remove those. Because it's a smooth incline, the normal reaction won't provide any friction, and therefore we can just remove it from the system. So the resultant force on A, as we can see, is T minus the weight times sine, or the weight component, which is the weight times sine alpha. Using F equals ma, we would obtain that equation. For object B, exactly the same discussion. Find the weight components, remove the weight, rid ourselves of the perpendicular forces, and therefore the resultant force is the weight component, which is the mass of B times G times sine theta, and then subtract T. And using Newton's second law, we obtain that equation. So here's our example. This time we've got some values in. Normal reaction, weight components, sine down the incline, cos into the plane, and therefore we can remove perpendicular forces. And so the resultant force is T minus 3g sine alpha, and that will equal 3 times A. For mass M, that's its weight, tension, normal reaction, components of weight, sine down the incline, cos into the plane, remove the weight, and therefore remove the perpendicular forces, and we have mg sine alpha minus T. Using Newton's second law, that resultant force equals mass times acceleration. That's our first equation. That's our second. Add the two together. The t's cancel. Now, what we've done here, we've taken the right hand side, we've taken a factor of A out, okay, and factorized to leave with m plus 3, and therefore we divide by m plus 3, and that gives us our expression for the acceleration. If our incline is rough, we've got the added complication of friction that comes into play. So, in this situation, we can see for mass A, perpendicular to the plane, R must equal the weight component, so m of A g cos alpha. Because motion will take place, and we can see from the diagram that B is going to be pulled downwards, and that will pull A upwards, therefore friction will oppose the motion of A, so friction will be acting down the incline on this left hand side. And because it's moving, because it's accelerating, that friction will be at its maximum, F max, which we know to be mu times R, and therefore that will equal mu times the weight component of A into the plane. Parallel to the plane, we have T minus the weight component minus friction equals mass times acceleration, and that's a heck of an equation. You're going to have to learn how to derive it. I wouldn't suggest you try and remember it. For mass B, perpendicular to the plane, once again, R equals the mass of B times G times cosine theta. Now this time, because B is moving down the incline, friction will oppose that motion, so friction will act up the incline. And it's at its maximum, so that friction is mu R. So we have that component acting up the incline. So parallel to the plane, we can rid ourselves of the perpendicular vectors, and we end up with the weight component down the incline minus the tension minus the friction equals mass times acceleration. And once again, it's a bit of an equation. You need to know how to derive it. Take your time, mark your forces on, resolve your forces, work out where friction should be, and then you'll be able to obtain those equations. So that was an equation of Newton's second law on mass B. That's Newton's second law on mass A, and we add them both together, you end up with that. Now clearly this all looks horrendous, letters all over the place, etc. I'm quite sure that in a question that you'll get in an exam, I'd be very surprised if you're asked to show something as complicated as this. I'd be very surprised, but you'll have values which will just simplify these. They'll look much easier.